Okay, so let's unpack this. We are diving deep into a piece of ancient mathematics. I mean, a tool that is so foundational, so elegant, really, that it underpins, well, the entire structure of modern digital security.
Right.
This algorithm, it was devised over 2,000 years ago, and it is still doing the heavy lifting for pretty much every secure transaction you make online. We are talking about the Euclidean algorithm.
It's amazing, isn't it? What really stands out here is that incredible leap from, abstract history to very practical daily application.
Mm-hmm.
We're not looking at some dusty theorem you sort of half remember from school.
Mm.
We're examining the engine that makes secure communication, cryptocurrency, online banking, that makes it all actually work.
Yeah.
And the source material, it just immediately positions the greatest common divisor, the GCD,
Yep.
as the absolute linchpin of the entire system.
The mission today is, I think, really crucial. We need to understand not just the mechanics of how this thing works, but why it is so incredibly powerful. And I think most importantly, why it is so fast.
Yes, the speed.
That speed is completely non-negotiable when you're dealing with these massive numbers stretching for hundreds and hundreds of digits that are just standard operating procedure in modern cryptography.
Exactly. And when you're dealing with numbers that long, the challenge, it shifts from being a mathematical curiosity to a raw computational bottleneck.
Right.
Your traditional, straightforward methods, they just completely break down. You need an algorithm that performs a kind of magic trick.
A magic trick. I like that.
It is. It's the trick of rapidly simplifying these gigantic problems. And specifically, we need this algorithm to enable what is essentially division in the very complex, very constrained environment of modular arithmetic.
And the GCD is the key to all of that.
It's the key that determines both solvability and, crucially, the invertibility of these numbers within those systems.
Oh, no.
It's everything.
So let's start with that natural bottleneck. I mean, when we first learned about the greatest common divisor in school, the standard method, it involved prime factorization. You take two numbers, you break them down into their prime factors, you find the primes they share, multiply them, and voila, there's your GCD. So why can't a super powerful computer just use that method for those massive 100-digit numbers we use in, say, public key encryption?
Because that approach requires prime factorization. And that mathematically is, it's the equivalent of trying to scale Mount Everest.
Yeah.
It's the computational Everest of number theory. And the source material makes this explicitly clear. Finding the prime factorization of these colossal numbers it takes far, far too long.
How long are we talking?
We're talking about potentially billions of years, even with the world's most powerful supercomputers, for the kind of numbers used in, industrial scale cryptography.
Wow. Okay, so that's a critical distinction. It's not just that it's slow, it's that it's computationally hard.
Yes. In fact, the entire security of widely used systems like RSA relies on that very fact. It relies on the fact that prime factorization is incredibly slow and difficult.
Right. If it were easy, the whole system would fall apart.
Precisely. If factoring a 500-digit number into its two large prime components were easy, we would have no digital security infrastructure, period.
So we have this fundamental problem. We absolutely need the GCD to do our higher level math.
We do.
But the intuitive brute force factorization method is completely out of the question. It would make real-time communication impossible.
It would.
So what's the elegant, time-tested solution that steps in to solve this colossal computational hurdle?
It's the Euclidean algorithm,
Yeah.
the EA. It's a blazingly fast alternative. It completely sidesteps the complexity of factorization by introducing an entirely different approach.
And its genius is in its simplicity.
In its simplicity and its foundation, which is codified in what the source calls lemma 1.3.1. This lemma is the core engine. It's the heart of the algorithm's unparalleled efficiency.
Okay, let's dedicate some serious time to this lemma then, because if that's the guarantee that allows for this blinding speed, we need to get it.
Absolutely. The lemma describes a very simple division step. It states that if you take two numbers, let's call them 65, you divide 63, you get a quotient, and a remainder, 12.
Okay, standard division. 63 plus R wall.
Exactly. Now here is the crucial kind of counterintuitive insight. The greatest common divisor of your original pair, the text GCD, text Y, is exactly the same as the greatest common divisor of the smaller pair, text GCD E Y.
Wait, I need to pause on that. That sounds almost too simple.
It does.
We're trading a complex problem involving this huge number, $6, for a problem involving and a rain in this tiny remainder, $3. Are you sure we don't lose any information about the common factors when we just throw out the quotient and move straight to the remainder?
We are absolutely sure, and that's the genius of Euclid. Think of it this way.
Okay.
Any number that divides both $62,000 must also divide 2, right?
Sure, that makes sense.
And since 60,000 quite plus our dollar,
Yeah.
that common divisor must therefore also divide $3 because it divides $6 and it divides 12. So it has to divide their difference, which is just 2.
Okay, that logic tracks.
And it works the other way, too. Any number that divides both gyro and $3 must divide confident plus RLI.
Which is just $6.
Which is $6. So the set of common divisors for the pair, 6y, is identical to the set of common divisors for the pair. And if the sets are identical, their greatest element, the GCD, must be the same.
That deepens the understanding. Okay, so we aren't guessing. We're relying on a proven algebraic identity that shows the set of common divisors is perfectly preserved. But why is that instantaneous substitution from 6y to ym too powerful for a computer?
Because the problem is instantly reduced. It's made smaller with every single step.
Right.
You started with 6 a bowl, which might have been massive. Now you're dealing with A in dollars, whereas Taylor's is guaranteed by the definition of a remainder to be smaller than yeah.
So you've simplified the pair of numbers you need to analyze without losing any information.
Exactly. And this iterative process guarantees that we rapidly converge on the answer. It's the ultimate mathematical simplification technique. Instead of looking for factors of huge numbers, we're just doing simple division and tracking the remainder. And the size of the numbers we handle just shrinks dramatically with every single step.
And that is the source of the speed.
That is the source of the speed. If your initial numbers had, say, hundreds of digits, within just a few dozen steps, you're down to single or double-digit numbers. We call this logarithmic time complexity.
Let's elaborate on that crucial term, logarithmic time complexity. For anyone listening, why is that so much better than the factorization method, which is what often considered exponential time?
It's a world of difference. Imagine you have a huge list of names, say 1 million entries in a database.
Okay.
If you used a linear search, you might have to check hundreds of thousands of entries to find the one you want. That's slow. Logarithmic complexity is like using a phone book or doing a binary search.
Where you open to the middle and immediately eliminate half the problem.
Exactly. You check the middle, you see if your target is in the first half or the second, you discard half the data, and you repeat. Every step eliminates a massive proportion of the remaining problem.
So if I use the Euclidean algorithm on a number that's twice as long, say 200 digits instead of 100, I don't need twice as much time or exponentially more time.
No.
I just need, what, a couple more division steps.
Yeah.
The time increase is almost negligible compared to how much bigger the input number got.
That's it. The running time of the algorithm grows incredibly slowly compared to the size of the inputs. This computational compression is the key to why Euclid's method, from ancient Greece, is still the undisputed champion for speed in modern computational number theory. It handles numbers with hundreds of digits in milliseconds.
And that speed is what makes secure real-time communication even possible.
Viable, yes.
Now that we understand that principle, that guaranteed reduction, let's walk through the actual mechanical procedure. This is the recipe from the source material, SATS 1.3.2. It's purely iterative, like a loop designed for a computer.
It's a machine built for division. And this purely mechanical, repetitive nature is why computers are so good at it. It's just the relentless application of that reduction principle we just talked about.
Okay, so step one, you start with two numbers, $6. Let's say 6 is the larger one, just for simplicity. We divide 6 by dollars.
And that gives you a quotient. We'll call it COLI dollars. And our first remainder are dollars. And that remainder is, remember, guaranteed to be smaller than the divisor dollars.
Step two, we now basically throw away the original big number, $6.
Oh, forget about it.
We take the divisor from the first step, which was yellow, and the remainder we just calculated, our $01. This new, smaller pair becomes our new input. So we divide R by a total dollar.
Which generates a new quotient, $2 and a new, even smaller remainder, $2.
And then step three is just repeat. We keep doing this. We always divide the previous remainder by the new remainder.
And every single step shrinks the problem, creating this rapidly decreasing sequence of remainders.
And we just keep cycling through this process until what's the stopping condition?
We keep going until the remainder is 0. That remainder is 0 is the definitive signal to stop. We've hit the bottom.
Okay, so if the remainder is 0, the division was clean. But where's the GCD in all this? What's the actual answer?
The GCD is the last remainder that was not 0. So if your final division step, say it's step Killier, gives you a remainder of shark, you look back one step.
You look back to the remainder from the step right before it, torcular. That last non-zero number is the greatest common divisor of your original huge numbers.
Let's just reflect on why this is so much better for a machine than factorization. It comes down to the basic operations, right?
Absolutely. Factorization involves complex searching, testing divisibility by lots of different candidates. It's conceptually demanding.
Yeah.
The Euclidean algorithm, though, it only relies on division, subtraction, and comparison. These are the most basic, the fastest operations a computer processor performs. There's no guesswork, just the mechanical execution of a short, fixed loop.
So it's a double win for speed. Not only does the algorithm require very few steps because of its logarithmic nature,
But each of those steps is also incredibly simple for a processor to execute.
that is the essence of algorithmic elegance. The ancient world gave us a method that just happens to align perfectly with the strengths of modern computing hardware. Even today, with all our high-performance computing, this 2,000-year-old iterative division is still the standard foundation.
Because nothing has proven to be significantly faster for this specific task.
Not for this, no.
Okay, here's where it gets really interesting. So we've mastered the standard Euclidean algorithm, the EA, to quickly find the GCD. But in the world of cryptography and, algebraic number theory, just knowing the GCD often isn't enough.
Right.
We need to use those intermediate calculation steps for a much, much greater purpose. And this is where we transition to the extended Euclidean algorithm, the EEA.
The extension is where this mechanical process of finding the GCD really transforms into a powerful algebraic tool.
Okay.
As the source material highlights, the goal shifts. We move from just finding the GCD to using those intermediate equations to express the GCD as a linear combination of the two original numbers.
It's often called the magic of reading backward.
That's a great way to put it.
When we did the standard EA, we generated a whole sequence of division equations. Now, if we read those equations in reverse and substitute back through them, we can achieve something pretty remarkable, expressing text GCD text YY in the form A times X plus B times Y.
And this result is much more than a computational trick. It's a fundamental pillar of number theory, formalized as Bezout's lemma.
Bezout's lemma.
This theorem guarantees that for any two integers, 6 Lori u, their GCD can always be represented as a linear combination of 6 Lori I using some integer coefficients as last dollar.
And these coefficients, the phi and the dollar that the extended Euclidean algorithm finds for us, they have a specific name, right?
They're called the Bezout coefficients. And while the standard EA is all about division and remainders, the EEA is focused entirely on this mechanical process of backward substitution to isolate and define those Euler coefficients. They are the true algebraic output.
They're the real prize.
They are. They provide the key of solving much, much harder problems later on.
We absolutely have to walk through the example from the source material Beispiel 1.3.3 to make this concrete. Let's find the linear combination for the GCD of 456 and 210. We should probably slow this down so everyone can track every substitution.
Excellent idea. We start with phase 1, just the standard EA.
Okay, I'll keep track of the equations. First, we divide 456 by 210.
Right. And that is $456 equals 2 times 210 plus 36.6 an hour. So our first remainder, 4 pander, is $36. Let's call that equation 1.
Got it. Next step, divide 210 by the remainder, 36.
That gives us $210 equals 5 times 36 plus $30. The next remainder, 2 divided 2, is 30. That's equation 2.
Okay. Next step, divide 36 by 30.
$36 is 1 times 30 plus 6. The remainder, 333, is 6. That's equation 3.
And the final step, divide 30 by 6.
$30, 5 times 6 plus 0 to which? The remainder is 0. We stop.
So the standard algorithm is done. The last non-zero remainder was 6, so the GCD is 6.
Perfect. The standard algorithm is complete.
Now for phase 2, the trick, backward solving. We need to express that GCD, which is 6, as a combination of our original numbers, 456 and 210. So we have to get rid of all the intermediate remainders, the 36 and the 30.
And we begin with the equation where the GCD first appeared. That's equation 3. It's the only one that defines 6 in terms of other numbers in our list. So we rearrange it to isolate the GCD.
Okay, so equation 3 was $36 equals 1 times 30 plus 6 segs. If we rearrange that, we get $6 equals 36 1 times 30 all 1.
That's our anchor equation. Now, we have to eliminate the 30. Where did 30 come from? It was the remainder in equation 2. So we look at equation 2 and we rearrange it to isolate the 30.
Equation 2 is $210, 5 times 36 plus 30. So $30, 210, 10, 5 times 36, 3.
Great. Now take that entire expression for 30, the whole $210, 5 times $36 part, and plug it back into our anchor equation for 6. This is our first big substitution.
Okay, so our anchor was $6. Okay, so there's $60, 1 times $30. We're replacing the 30. So it becomes $6 equals 36 1 times 210 5 times $36.
Exactly. Now let's do the algebra carefully. Distribute that negative sign.
Right, so we get $6, $36, 210 plus 5 times $36.
And now we can group the terms that involve 36.
Okay, we have 136 at the start and then 5 more of them. That gives us 6 36s. So $6 is 6 times 36, 1 times $210.
We're one step closer. But we still have that remainder, 36, in our equation. We need to get rid of it. Our final goal is to only have 456 and 210.
So we need to eliminate the 36, and that came from the very first step, equation 1.
Right.
Equation 1 was $456 equals 2 times $256, 2 times $210.
And that's our final substitution. We plug this entire expression for 36 into our current equation for 6.
Okay, so the current equation is $6 is 6 times 36, 1 times 210. We replace the 36, so $6 and 6 times 456, 2 times 210, 1 times 210.
Now, just distribute that 6.
Okay, be careful with the signs here. We get $6 is 6 times 456, 2 times 210, 1 times 210.
Good.
Which is 6 times 456, 12 times 210, 1 times 210 now.
And finally, just combine the terms that involve 210.
We have negative 12 of them and then another negative 1, so that's negative 13 of them. The final linear combination is $6 equals 6 times 456, 13 times $210.
And we've done it. We've completed the process. We found the Bézout coefficients. Here are the 6 and Bézout's negative 13. The extended Euclidean algorithm uses the staggering efficiency of the standard algorithm to find the GCD, and then by just meticulously working backwards through these substitutions, it reveals that guaranteed algebraic connection.
It's purely mechanical.
Purely mechanical. And the fact that these coefficients are guaranteed to exist by Bézout's lemma is the powerful theoretical takeaway here.
We've spent a lot of time on the computation, and rightly so. That's the practical use in crypto. But Bézout's identity, this ability to write the GCD as x plus bi, it isn't just a nice trick for calculating $. It has this profound theoretical payoff.
It does. It underpins fundamental proofs that define the very nature of numbers. The capacity to express the GCD as that linear combination is essential for establishing some core, non-trivial properties of arithmetic. And this brings us to a foundational concept, lemma 1.3.6 in the source, which defines a key, exclusive property of prime numbers.
This lemma states that if polemis is a prime number and pidol divides the product of two numbers, 6 times yr, then Piley must divide 6 dollars or plenas must divide a 50.
This is a property we often just take for granted, but it is deeply, deeply exclusive to primes. It's what separates the foundational building blocks of arithmetic from composite numbers.
And the question is, why do we need the algebraic leverage of Bézout's identity to prove something that seems, it seems intuitively obvious?
Let's use the contrast the source gives us to illustrate why it's not so trivial.
Okay.
Take the number 6. It's not a prime number. If this lemma were universally true, 6 would have to follow the rule.
But it doesn't.
It fails. Consider the product $4 times 99. That's 36.
And 6 clearly divides 36.
It does. However, 6 divides neither 4 nor 9 individually. That failure, the ability to divide the product without dividing either of the factors, is the mathematical confirmation that 6 is composite. Only primes have this special property.
So if the rule seems trivial, it's only because we're so used to operating in systems built on primes. But the proof requires rigor. Why exactly does the proof that primes must divide one of the factors need the extended Euclidean algorithm?
It's all about creating an algebraic contradiction. When you prove lemma 1.3.6, you typically use a proof by contradiction. You start by assuming two things. First, that pass is a prime that divides 6 times 1d1.
Okay.
And second, you assume that pass does not divide $6.
And if pass is a prime and it doesn't divide $6, what's the only possible greatest common divisor between them?
Their only common divisor can be 1.
They're coprime.
Exactly. So text GCD x equals in the 1. This is the critical starting point.
And once we establish that the GCD is 1, we can immediately call upon Bézout's lemma.
That's the move. If the GCD is 1, Bézout's lemma guarantees we can write that 1 as a linear combination of two $. So $1 equals A times P plus B times a 1s. The out of the coefficients we'd find using the EEA.
So now we have this equation that algebraically links 3 Ohs to Euler. How does this equation force powers to divide U?
The next step in the proof is it's elegant. You take that entire equation, $1 is A times P plus B times U, and you multiply everything by I.
Okay, so that gives us y i.e. equals A times P times Y plus B times X times Y.
Now, just look at the terms of the right side. We assumed at the very beginning that p divides the product, 6 times y.
Okay.
So look at that second term, y times x times y.
Yeah.
Since we know p divides x times y, then p must divide that entire second term.
Right, makes sense. And what about the first term, A times P times Y, Ellen?
Well, that term obviously contains Ballar's as a factor, so people must divide the first term as well.
So if P divides both terms on the right side of the equation,
Then it must divide their sum.
and their sum is just yeah, so P must divide yeah.
And that completes the proof. Starting with the assumption that P's doesn't divide $6, we use the algebraic leverage provided by the Bezout coefficients to prove that Pondyol must divide UR.
It's a clean, airtight proof.
It is. And the Bezout coefficients, which we discover through that mechanical backward substitution of the EEA, they are the non-negotiable algebraic tool we need to manage that logical contradiction and establish the fundamental nature of primality.
So this is far more than just abstract theory. It's a powerful demonstration that the efficiency of the Euclidean algorithm is actually the engine that drives our deep theoretical understanding of what defines a prime number itself.
The building blocks of all mathematics, yeah.
Okay, now let's close the loop. Let's return to the high stakes of modern computing. We need to connect the ancient EA and the algebraic power of Bezout back to modular arithmetic.
Right.
This is the math that governs everything from hashing functions to public key encryption. And the core question we started with was, when can I divide in modular arithmetic?
And division in modular arithmetic or modular calculation, it's not the same as normal division. You can't use fractions. If I want to divide by a number of 6 modular colors, what I actually have to do is multiply by its multiplicative inverse.
So I need to find some number, let's call it 8, such that when you multiply it by 6 egal, the result is congruent to 1 modulo galars. That number 8 is the inverse.
That's the inverse. And in standard arithmetic, every non-zero number has 1.
But not in modular arithmetic, and this is where things get tricky and where the stakes are highest for crypto.
Exactly. Not every number has an inverse modulo colors. So how do we know which ones do? The source gives us this incredibly powerful efficient decision rule in SATS 1.3.9.
Lay it out for us. What's the rule that separates the invertible numbers from the non-invertible ones?
A rest class $6 is a unit, which is just a fancy way of saying it's invertible, if and only if $6 and the modulus dollars are coprime.
They share no factors other than a 1.
That's it. Their greatest common divisor, text GCD, must be exactly 1.
That is extraordinarily elegant. We don't have to test multiplication across the whole system. We just run our lightning-fast Euclidean algorithm on $600. If the GCD is 1, the inverse exists.
And what if the GCD is greater than 1, say a 2 or 5 or 100?
If the GCD is greater than 1, the number $6 is what's called a zero divisor. It cannot be inverted.
And that contrast is the entire decision-making process for modular division. We avoid having to randomly test candidates or draw out these huge, complex multiplication tables. We just calculate the GCD. It's a monumental efficiency gain for any real-time system.
But the real magic, the part that ties this all together and makes the EEA so foundational for cryptography, is that when the number is invertible, when that GCD is 1, we get the inverse. What, almost for free?
You get it almost for free. That's algorithm 1.3.7. It shows this seamless transition. If we know the GCD is 1, the extended Euclidean algorithm immediately gives us the Bezout identity for the pair 6 colors.
Which, since the result is 1, is just the equation. 1 dahlia times x plus b times k.
Right. And remember, the EEA already calculated those coefficients $8 for us during its backward substitution phase.
So we ran the EEA to find the GCD of 1, and in the process, it just automatically spits out $18. Now we apply the final essential modular step. We look at that equation through the lens of modulo dollars.
Look closely at that second term, the bile times k. This term is, by definition, a multiple of the modulus dollar. And when we're working modulo dollar, any multiple of dollars is just congruent to 0. It vanishes. It falls away from the equation entirely.
And that simplifies the equation dramatically. If $Baller times k becomes a 0 modulo dollars, we're left with $1 equivalent times x pay mard.
And that's the payoff. By the very definition of a multiplicative inverse, that coefficient etal, the one the extended Euclidean algorithm calculated for us, is the inverse of $6 modulo dollar.
That is truly elegant. The The speed and efficiency of calculating the GCD are repurposed into the speed and efficiency of finding the inverse. This is the foundational step that enables secure communication. The ability to perform division quickly is what allows for all these complex key calculations to happen in real time, validating identities and decrypting messages without any delay.
Let's just solidify this with the final concrete example from the source, example 1.3.112.
Okay.
We're working in the context of integers modulo 1,000. So the modulus, KO, is $1,000. We want to know if the number 13 is invertible, and if it is, what's its inverse?
First step, check the GCD. We need to find text GCD 13, $1,000.
Well, 13 is a small prime. 1,000 is just 103.3, which factors into $23 times 503.3.
And 13 shares no prime factors with 1,000.
So we immediately know their GCD is 1. Yes, 13 is invertible.
Now we run the extended Euclidean algorithm on 13 of the 1,000. That process, which for a computer is instant, yields the Bézout identity. The result it gives is $1 is 77 times 13, 1 times $1,000.
And that is the equation we care about. And now we apply the transformation. We look at this equation modulo 1,000.
The $1 times $1,000 term, it just vanishes because it's a multiple of the modulus.
The equation collapses to $1 equiv, 77 times 13 bxmol.
The inverse is found. The number 77 is the multiplicative inverse of 13 modulo 1,000. So if you wanted to divide by 13 in this system, you would just multiply by 77 instead. The 2,000-year-old iterative division process just delivered the key that unlocks division in a constrained, modern digital system.
It's that simple, once you understand the underlying mechanism. So we began this deep dive looking at this massive computational challenge, these gigantic numbers used in cryptography where factorizing is just an insurmountable hurdle.
Right.
And we found our solution in the Euclidean algorithm, an ancient iterative division process that is just blindingly fast because it continually reduces the size of the numbers it's working on in a logarithmic way.
But the true power, I think we found, was in the extension, the extended Euclidean algorithm. It takes the speed of the standard method, and then it extracts those necessary Bézout coefficients and the dollars through that meticulous backward substitution.
And those linear coefficients, they are the algebraic leverage point. They're the absolute key to solving problems in modular arithmetic. They transform the simple existence of a GCD of 1 into the actual calculated multiplicative inverse of modulo dollars.
Which is the essential step.
It's the essential step that unlocks modular division and makes sophisticated, secure communication computationally feasible and lightning fast.
So think about this the next time you connect securely to a website or send a financial transaction that's protected by RSA or Diffie-Hellman or any similar protocol. The incredible speed and the ironclad security of the modern internet often depend entirely on calculations performed quickly with numbers hundreds of digits long. The fact that the foundational magic trick enabling this entire digital world, the ability to perform basic division, is a simple, elegant sequence of iterative divisions devised by Euclid over 2 millennia ago. It's just a testament to the enduring foundational power of classic mathematics. We're relying on geometry developed in Alexandria to secure our virtual lives today.